I'm back at Lakeside School, and I'm in the chemistry lab, as you can see. Now, look around you and try and count how many different sorts of materials you can see. 10 easily, 100, not too hard. And if you counted really carefully, well, look at all these materials here. You could probably come up quite easily to 1,000, 10,000, or maybe even 100,000. That's because in a universe with 100 elements, you haven't just got 100 different materials. Those elements can combine with each other in a huge number of different ways to form millions and millions of new materials, all the materials we see in the world around us. All these new materials eventually combine to create entirely new astronomical bodies. The most important by far for us, of course, is our home planet, the Earth. But before we describe how the Earth and the other planets of the solar system was created, there's a little problem we have to take up. You'll remember from the last unit, we saw that all those new elements that were created made up only 2% of all the atoms in the universe. Yet if we look at our Earth, we'll find that 90% of the Earth is made up of elements like iron, oxygen, silicon, magnesium, and other elements created in supernovae and dying stars. So how did they get concentrated like this to form planets and bodies like that? Now, before I give my answer, I'd like to ask if you have any ideas about how that might have happened. To answer these questions, we must think about chemistry. Now, chemistry is all about how different elements link up, how their atoms link up to form what we call molecules. How atoms link up depends very much on the arrangement of their electrons. Some elements, such as helium, are very, very stable. They hardly ever link up with other atoms. In fact, they're known as the noble gases. It's as if they're too snooty to join up with other atoms. You'll find them on the right side of the periodic table, by the way. But most atoms really like to link up with other atoms. We say they are reactive. Hydrogen and oxygen, for example, are always looking for chances to link up with other atoms. If you see burning or you see a flame, what you're really seeing is oxygen linking up really violently with other atoms. It's very reactive indeed. Now, when atoms join together, we call them molecules. Each molecule has its own distinctive qualities, which may be very different from the elements of which they're formed. For example, hydrogen and oxygen are both gases, but when they combine, they form a very, very familiar liquid, water, H2O. And water has qualities completely different from both hydrogen and oxygen. Different types of molecules also have different types of bonds. Some bonds are extremely rigid, but others are very flexible. Some are very strong, very hard to break. Others are very easy to break. So there's a huge variety of different types of links between molecules. Carbon, for example, can link up with itself to form diamonds. Now, in a diamond, the bonds are extremely strong and extremely rigid, so a diamond is very tough indeed. But carbon atoms could also link up with themselves to form a very different material, graphite. Now, graphite is the lead in a pencil. It's very soft stuff indeed. So different bonds make a lot of difference. Now, these different types of links, different types of bonds, mean we have a huge variety of different types of materials. That's what explains the huge variety of these materials. But note that it's mostly elements other than hydrogen or helium that make up these chemicals. And that's one reason why when we talk about rich chemistry, we're talking mostly about that tiny 2% of elements from the periodic table. Atoms began to form molecules even in deep space, in the clouds of matter ejected by supernovae and dying stars. How do we know this? Well, using spectroscopes, we can tell what elements and what chemicals are out there. And we know there's water, plenty of ice, carbon dioxide, ammonia, acetic acid, a whole range of simple molecules that are very familiar in daily life. There are also lots of silicates. Silicates are molecules made from silicon and oxygen, and they make up most of the rocks in the Earth's crust. Now, in space, these molecules, which were pretty simple, by the way, they included 10 to 20 atoms, at most 60. In space, these molecules couldn't do a huge amount of interesting stuff. But around newly born stars, it turns out you could do a huge amount of interesting stuff with these molecules. In fact, you could make planets. To see how this works, what we're going to do is we're going to travel back in time 4.5 billion years, and we're going to zoom in. We've been looking at the universe so far in this course. We're going to zoom in on one rather average galaxy, the Milky Way. We're going to zoom in on one tiny part of it, and we're going to look at the birth of our solar system. Now, our sun formed, like any other star, from the collapse of a cloud of matter under the pressure of gravity. That collapse, like many others, was probably triggered by a huge supernova explosion somewhere in our region of the Milky Way. And that supernova explosion also seeded this cloud with lots of new materials from other supernovae and from dying stars. As the cloud collapsed, it began to spin, like a spinning pizza dough. And as it spun, it slowly flattened out to form a disk. Now, this is something that happens throughout the universe, which is why the universe is full of flat disks, from the Milky Way itself to our solar system, even to the rings around Saturn. Astronomers call this sort of disk a protoplanetary disk, or a proplid. Now, as the proplid that eventually formed our solar system began to collapse, at its center it got hotter and hotter and hotter until eventually fusion began and our sun was born. About 99% of all the material in the proplid went into the sun. 99.9% in fact. That leaves 0.1% for the rest of the solar system. All that stuff was orbiting around the sun, and amazingly that tiny residue is what formed all the rest of the solar system. Now let's begin by looking at the outer gassy planets and how they were formed. The intense heat of the young sun drove away gassy materials from the inner parts of the solar system, and above all, it drove away a lot of hydrogen and helium, leaving that as a region deprived of hydrogen and helium. And all that gassy material gathered further out in the solar system and eventually condensed to form the gassy giants. They are Jupiter, Saturn, Uranus, and Neptune. Now, they contained about 99% of the leftovers. So what we're left with is a tiny residue of a tiny residue to form the inner rocky planets, including our Earth. Closer to the Sun, from that tiny residue of a residue, you find material orbiting in the inner orbits. And that material is less gassy, there's more sort of solid stuff. You have little dust motes that eventually will gather together through electrostatic forces or collisions to form little rocks. You have particles of ice that will eventually form snowball-like objects, and eventually they form things like meteorites or asteroids, and they're getting bigger and bigger and bigger, and they're colliding with each other. And in each orbit, you eventually get large objects that finally sweep up through their gravitational pull everything else that's in the orbit. And so eventually, over 100 million years, in each orbit, you have a rocky planet. Now this process is called accretion. It's extremely violent. There's a huge amount of space stuff smashing into other space stuff. And if you want to be persuaded how violent it was, get out a pair of binoculars and look at the moon one night and look at those craters. Those are evidence of how violent the process of accretion was. Our moon was probably created when an object, perhaps the size of Mars, collided with our Earth, our young Earth, and it gouged out a huge chunk of the Earth, and that stuff orbited around the Earth and slowly accreted to form the object that we call the moon. So in this way, through these processes over about 10 to 20 million years, our solar system formed. And we end up with a solar system that has inner rocky planets in the inner orbits, these large gassy planets in the outer orbits, and woven through them lots of space debris. It includes meteorites, asteroids, and comets. No one knew if there were any other solar systems anywhere else in the universe. It was quite possible this was the only solar system in the universe. But in the last 15 years, there's been some quite magical astronomical research, a lot of it based on satellite telescopes, such as the Kepler satellite. And what we now are able to do is actually see other solar systems. They vary hugely. But we now know that solar systems are actually very, very common indeed. And strangely, what that does is it rather increases the chances that out there somewhere there is life of some form. So exciting is the science, by the way, that I even have an app on my phone that tells me all about the most recent discoveries of so-called exoplanets, which is what planets around other stars are called. let's return to the problem we began with in this unit. How is it possible from all these rare new chemical elements to create entirely new things? And I hope by now we have the beginnings of an answer. First, we saw that chemistry links chemicals to form simple molecules, a whole range of new materials. They're floating through space. And secondly, we saw that in the environments, and we can call them the Goldilocks environments, around newly formed stars, those molecules get smashed together. They get brought together by chemistry and by gravity and by electricity to form objects like dust motes, meteorites, asteroids, and eventually planets and solar systems. Now, we regard the creation of solar systems as the fourth great threshold in this course. And that's because planets, and in particular rocky planets like our Earth, are significantly more complex than stars. They are more complex because they have more internal structure, but they are also much more complex chemically. They contain a much greater diversity of materials. Okay, now I've worn this lab coat throughout the whole lecture, even though I'm a historian. I think it's time to take it off. But I hope you're beginning to see that what's happening is that our universe is getting more complex, more diverse, and more interesting.